Okay. Hello, everyone. I'm Maura Pintor, and I'm assistant professor at the University of Cagliari. In today's event of the Machine Learning Security Seminar Series, we have Ilia Shumailov that will be presented very soon. I want to share some information before we start. First of all, the meeting is live streamed and recorded. You will find it after in our YouTube channel. If you want to ask questions, feel free to raise your hand during the meeting, and we prefer actually questions from the Zoom call. Otherwise, feel free also to type some comments in the YouTube chat, and we will check them if there is time left. Follow us on Twitter, LinkedIn, Eventbrite, or all the links you can find in the website that Luca just pasted in both chats. If you want to receive more updates on the events that we organize. And if we want to strengthen your background in machine learning security, we also have a free course available in our YouTube channel that teach you all the basics of machine learning security, and you can find it easily in the YouTube channel. And I would like to thank all the people who help me organize every month this series. So thank you all. And now I leave the stage to Luca, who will introduce the speaker for today.
Thank you, Maura, so much for the introduction. So today we have Ilia Shumailov, which he holds a PhD in computer science from University of Cambridge and specializing in machine learning and computer security. During the PhD under the supervision of Prof Ross Anderson, Ilia worked on a number of projects spanning the fields of machine learning security, cybercrime analysis, and signal processing. Following the PhD, Ilia joined the Vector Institute in Canada as a postdoctoral fellow, where he worked under the supervision of Prof Nicolas Papernot and Prof Kassem Fawaz. Ilia is currently a junior research fellow at Christ Church, University of Oxford, and a member of the Oxford Applied and Theoretical Machine Learning Group with Professor Yarin Gal. Thank you for being our host. The stage is now yours.
Okay, should be good. Can you hear me? The slides are there.
Yes.
The slides are moving.
All good.
Yes. Wonderful. Thank you very much for inviting me. Very happy to be here. Today we're going to be talking about something relatively exciting, at least exciting for some of us, namely me. I want to mention a few things first. So first of all, not a native speaker. So if suddenly you discover that something is not making sense, there is a high chance that I'm just saying something that doesn't make sense. So do let me know, and I'll try rephrasing. The second thing is I am severely underslept. So sleep deprived. So if I'm saying things that don't make sense, please let me know. Same as before. And the last thing is I can only really see my slides and I cannot see people. So if somebody's raising a hand, I would just wanted to ask the organizers to keep track of this.
Yes.
And again, if there are any questions, please disrupt the talk and let's argue. So this is great. Okay, cool. So today we're going to be talking about TCB in machine learning, namely the trusted computing base, something that is extremely important, but is not really very much talked about. Right, so a few words about me. Thanks a lot for introducing me. You can never know. But basically, long story short, spent a bit of time in Cambridge working with Professor Ross Anderson, one of the founders of the field of computer security. Then I joined Vector Institute to work with Professor Nicolas Papernot and Kassem Fawaz, where I looked quite a bit at privacy inside of machine learning and some of the aspects of security of machine learning. And then I managed to get a position, one of those fancy fellowships at the University of Oxford, where I am currently a junior research fellow for another 4 days. So should be fun. You can find me on Twitter just below. Right, so without further ado, the sun is shining, the grass is green, it's so nice outside. And it was about the same, you know, every other day you wake up and it's really nice. And then once, bam, we see the news and we discover vulnerabilities, security vulnerabilities all over the place. Very recently, we had to deal with something called Log4j vulnerability. Log4j is one of those. For those who are not familiar with this, Log4j is a framework that is used for, as you can guess, logging. And logging is one of those fundamental primitives that we rely on in computer science all over the place. And Log4j is practically used everywhere, and, well, was practically used everywhere, and was one of those standard pieces for making sure that you can have some sort of accountable software, you can keep track of what's going on in your system, and you can debug stuff. So anytime you wanted to log something out, you would rely on this framework. So once upon a time, people discovered that actually you can rely on this framework and to manipulate the whole of the system. They found a bug inside of it, easily exploitable, where you could practically get arbitrary code execution out of it. And it was really easy to exploit, making it extremely devastating all over the place. And the important thing was that Log4j was one of those fundamental pieces in the overall supply chain of our computing. So millions of devices affected. And it took a very, very long time to get it fixed. And the important thing, the reason why I'm bringing this up is because when we talk about such complex things as supply chains in software, we have to inevitably go as deep into our technical stack as we can and include every single bit along the way. So Log4j, something as primitive as a library that is used to keep logs in place, is an extremely crucial and important component. And your overall security of the system is going to depend not on fancy security firewalls and stuff put on top of your application, but also something as simple as a logging utility. So now we ask a few questions. So thinking about this Log4j, what is trust? Why do we trust? Simply, and then once we understand why we trust, what do we trust? And then once we outline what we trust, we ask a question, what should we trust? And once we figured out this list, we go into the question, why do we even trust that? All of those questions are extremely important. One flows out of the other one. And it all depends on this small world, trust. When we go and try and define it, again, I'm going to be very much Cambridge security PhD student and refer to a book by Professor Ross Anderson, where so I stole the slide from one of the computer security lectures that we teach in Cambridge. This is one of the very first slides from the very first lectures from the software security engineering course that was once designed by Ross, where we talk about the terminology we use. And trust is one of those fundamental pieces. And there are very many different definitions. Usually people joke about this definition of a warm, fuzzy feeling inside of you. But actually, so the commonly understood definition is a trusted system or a component that is basically that can break your security policy. So the way to interpret this is there exists a sort of a security policy, so some sort of a high-level definition of what you expect out of your system. There is there are a few very high-level phrases about what your system is supposed to be doing, what it's supposed to achieve, the users, and the sort of principles involved in your system. And with all of this in mind, you can then define the components involved. And then for the components that you trust to operate correctly, those are the components which basically you can't really put some sort of constraints on top of them. You cannot defend against them misbehaving. And because of it, you inevitably have to trust. So trust is about being unable to actually secure something. It's being unable to put constraints on a component enough such that inevitably you have to trust it. It's worth mentioning that it's not always because it's impossible to defend something that you have to trust it, but rather sometimes it's just not really feasible to do this. And then once we define what trust means, within the computing space, we can go on to the trusted computing base. So this is a screenshot from a NIST website. And trusted computing based here refers to basically everything there is that you trust, anywhere from the application level onto the hardware, has to go into your trusted computing base. Basically, if there is any component in your supply chain or in your general technical stack that inevitably you have to trust, because you cannot put protection mechanisms to make sure that it operates correctly. It has to be listed in your trusted computing base. You have to understand that this is what it does. This is what potentially it can do. And this is the sort of damage it can do to you if it decides to break this trust. All of this depends fully on you defining what a security policy is, and you defining what inevitably you have to trust, and all of the security mechanisms that protect the other components. And then, bam, you have your trusted computing base. This is the TCB. Okay, so now let us turn to this wonderful topic of discussion. What is this trust in machine learning? What do we trust? And then all of the subsequent questions we've seen before. And importantly, I think in this talk, it would be great if we could somehow outline what a machine learning TCB even looks like. What is it? What is the beast, and what does it consist of? And then, obviously, once we outline this, we would want to ask a question of how one reduces this trusted computing base and how do we build defenses around it. And hopefully, I'll give some sort of an answer towards the end of this question. I think before going any further, it's important to note something. Something that is commonly understood, but people don't talk about it enough. And that is, when we talk about people who practice computer security in machine learning, and then we talk about a group of people who practice machine learning and computer security, those two groups are usually rather disjoint. And because of it, there is a group of people who worry about theoretical guarantees of the sort of classifiers we build, and we say within this community, for example, we would say that adversarial examples are an example of security, because you have a component and somebody manipulates component. But then you would take adversarial examples and you go to the community of computer security practitioners who deal with exploits on a daily basis. They look at adversarial examples and they will just say, no, this is not security. It has nothing to do with security, because security is about a kid somewhere who runs Metasploit and breaks our systems, rather than thinking about some machine learning component, which is a minor part of the pipeline, which is not even exposed to anyone. And this is a massive problem, because machine learning obviously does not exist by itself. There is a massive computing infrastructure, as is shown in this slide, where machine learning is like a tip of an iceberg. This is this flashy, wonderful topic that sits above the surface, and we look at it and we are all amazed at all of these wonderful things that an LLM can do. And then in order to make it work, there is massive, massive stack of computing infrastructure, something that we have to deal with. And inevitably, it contributes to security a lot more, arguably, than just the machine learning itself, right? And as long as we have those two communities of people, ones that are securing the computing infrastructure and then the machine learning people separately, we inevitably end up having problems at the intersections, because given how widespread computing infrastructure is and how crucial it is, and given that majority of attacks do not actually target the machine learning system in reality, but rather they target the computing infrastructure, people just do not really take machine learning seriously, and or they don't really think about the interaction of machine learning when it becomes a part of the said computing infrastructure or a part of your technical pipeline. But the important thing to take out of this is that computing infrastructure is massive. So one summer last year, we were sitting with a number of colleagues, and another slide. Just to motivate this a little bit further, I wanted to give a few examples of the classical software vulnerabilities that are found within the space of machine learning. So the leftmost example is an example from a year ago, where somebody posted on Reddit that they discovered that inside of the ImageNet dataset, one of the most commonly widespread datasets, the image dataset, the image benchmark, they've discovered an image there which has malware inside of it. Basically, there is a piece of an exploit there that targets a very specific vulnerable image viewer. So if you had this image viewer and you would, by mistake, open this one image out of the whole data set, you would be redirected to a domain. Domain expired long ago, so worry not. Somebody bought it. There are no exploits there anymore. But it's quite just amusing and bizarre that there exists, the most widespread data set out there, and we have actual malware inside of it. At the same time, if you monitor the CVE is reported on top of machine learning libraries. The example in the middle shows the CVE from 2018, where chaps discovered that there are buffer overflows inside of TensorFlow, one of the most widespread libraries for machine learning. And then similarly, nowadays, Google's guidelines basically says if you are loading TensorFlow models, load them inside of jails, load them inside of sandboxes, because if you don't, you are going to be owned, because your models are practically programs. They have, many of them actually have instructions written inside, like literal raw instructions. So do not ever think about running machine learning outside of sandboxes. If you do that for research purposes or any other purposes, attackers will take control over your machine up to arbitrary code execution. This is the worst of ideas. And all three examples you see on the slide actually come to interaction with humans because of machine learning. They are there because of machine learning. So clearly there exists this layer between machine learning and security that has to be looked at. Right, so now, we were sitting the other day with a bunch of colleagues, and we wanted to outline what a trusted computing base even looks like. So we wanted to see all of the necessary steps involved in training a machine learning model or deploying a machine learning model, and we decided to go step by step in it. After, I don't know, an hour of discussion or so, we came to realize there are so many different components involved. And in this particular example, I just listed a few of those, but this is obviously not an exhaustive list. And each one of the words that you see on the slide can be further broken down into other techniques people rely on, or algorithms that are used to make it work. So we decided to summarize it in one way or another. So what you see here on the slide is a very, very high-level flow diagram that is featured inside of the paper listed on the bottom. It was produced by Tim Clifford, who was one of our summer interns. And as you can see, there are a number of boxes on the slide. So the leftmost red box talks about data. This is something that all of the machine learning engineers are very familiar with. You start off with data, you do some sort of cleaning of your data, you wash it, you create a data set. Once you've created this data set, you perform the splitting of the data set into training data, test validation. Then you perform some sort of pre-processing. Sometimes this pre-processing is stochastic. Once you've done this, you do some sampling, either full-on sampling, uniform sampling, or some sort of other biased representation of those samplings. Once you've done this, you're outside of this data realm. You no longer touch the data, and you start doing other things. So, for example, the yellow box to the right of the data box is talking about architectures. So this is where you pick an architecture of choice. Very often nowadays, you have to also tune your hyperparameters of the model. So think about this as network architecture searches and so on. Once you have this stuff in place, you then initialize your weights. You do some training hyperparameters. Again, you choose them arbitrarily, usually. Then you have your weights. You optimize your weights for hardware, as an example. And then this is a point where you get to runtime. So the pink box on the bottom and the blue box to the right, outlining runtime components and compilers, they are massive. They're humongous, but they usually fall outside of the realms of machine learning, of what we understand as machine learning. Every time people talk about reproducing, for example, model training, they talk about data and architectures they used and the sort of hyperparameters they use. Nobody's talking about compilers. Nobody's talking about optimizations involved in compilers. Nobody's talking about how it happened. The lowering from the graph IR representation falls into operator IR. And then once it hits this, nobody's talking about the actual backend intermediate representation and compilation. When we talk about deployment, again, nobody's really talking about compilation and the security problems that happen at the compilation stage. And once you have compiled, so it's important to note that compilation can take very different forms. For example, when you train your model, you don't actually really compile it. Whereas if you are doing deployment, your compilation stage will look very differently. And similarly, parts of your network are going to be ahead of time compiled. very different, depending on how you perform deployment or training, you'll have differently built operating systems, your runtime graph will be changing, your hardware will be taken into considerations and so on. But the important part here is this seemingly simple process of developing machine learning applications is actually extremely involved. There are a lot of moving pieces. All of your infrastructure, which we understand as this blue box and the pink box, are massive. Like if you think about millions of lines of code, millions lines of instructions, they are very, very large. And this is what makes our black box model work when we send a question to ChatGPT or OPT or whatever model. All of those steps must have been taken, and all of those steps inevitably influence security. So in this talk, I didn't quite want to talk in details about any one of the papers in particular, and any sort of exploitation in particular, but rather I wanted to give an overview of things that can go wrong once you start thinking about machine learning as being a part of the system and start asking questions. What things do we inevitably trust? And unfortunately, we cannot do anything about them, but just trust. I'll cover a number of works. Some of those are mine, some of them are not mine. Some of those I contributed to as main author, some of them are mostly done by somebody else. I'll talk about randomness, and I will talk about model architectures and backdoors. And then we'll try and summarize and talk about the trusted computing basis. So first, what do we do when we trust randomness? So randomness is a little bit of a tricky one in that there is no really definition of what randomness is, and there is no real definition of what a random sequence, like if you say a random sequence of numbers is. We have some sort of an expectation of what it means, but it's an age-long debate. So in this part of the talk, I'll give example of 3 attacks that can happen because of randomness, and that rely on randomness as the major source of the actual vulnerability against the machine learning model. So in this work, this is manipulation of stochastic gradient descent with data ordering attacks. This paper appeared at NeurIPS. We showed that one can change the order in which you supply data into a machine learning model, where you do not change the data at all. You do not touch so the integrity of the data is preserved. But by changing the order in which you supply data, you can influence the final outcome of the model. So the best way to think about this is on this plot. The green range shows 10 epochs of training, and this is basically prediction on a data point of your choice. So you pick a data point and say, oh, I want this data point. In this particular example, take class 3. And you just normally train on it, and you can see that the prediction is, well, the biggest line out of the ones shown on the graph. And then in the first 10 epochs of training, this is truly clean training, so nothing is happening there. And then what we do for the rest, for the 95 batches of poison clean data with clean labels, what we do is we pick data points in a biased way. So basically, we say we want to get class X, so in this case, class 3, and then we compute the gradient update that we want our model to have. So we take our poison data point, we say we want class 3, we compute the gradient update. And then what we do then is we try and look for data points, the clean data points that when sampled together in a batch result in a gradient update that is very similar to the one that we would have gotten if we trained with the data point that we want misclassified. And what we observe that when we do this, when we pick data points so that they give us gradient updates that are close to the ones that we would want, the adversarial gradient update, we actually can influence the prediction of our model. And what that kind of means is that you can approximate a given data point, which does not really exist in your training, with data points which exist in your training. And this is because we have stochasticity inside. So the stochastic gradient descent itself, the stochastic part of it, implies that the data points are sampled uniformly. out of all of the data points you have available. And if you break this assumption that the data points are sampled uniformly, you actually end up in cases where you can introduce behaviors into your models which actually should not even exist there. And we show in the paper that you can introduce backdoors into papers, and this works somewhat reliably in some settings. And you don't necessarily need to even have access to the true gradients of your model. You can use another model where you share the implicit bias with it. And you nevertheless can actually introduce backdoors. Similarly, we show that actually we can do a similar thing with augmentations. This is a paper mostly run by Joseph, who was also one of our summer interns, where we looked at ways that people commonly perform automatic augmentation. So there are frameworks like AutoAug, where people have spent quite a lot of effort trying to embed all of the possible invariances that you would expect your system to have. So think about it this way. You're trying to deploy a model to be used in a car, and you know that within the space of a car, you expect your models to be invariant to, say, rotations. So if a camera is shifted a little bit, like in a box by up to 15 degrees, you still expect your camera to work quite well, right? But very often you do not actually want to define what your augmentation looks like. So you will find plenty of frameworks out there, which basically, in essence, what they have is they have a set of augmentations themselves. So think about the different types of noise that you expect your model to be resistant against. And then all you need to do is you grab this component, this auto augmentation component, you plug it inside of you, in front of your network when you sample the data. And then what you can do is you can then basically rely on this augmentation component to give you invariance of your choice. In this particular work, what we show is that many of those augmentations depend extremely heavily on randomness itself. So, for example, imagine you're applying Gaussian noise to the image of your choice because you want to be resistant to Gaussian noise. The actual noise that you have sampled is going to be very different. The variance is usually quite large, especially when you start considering other types of invariances. Like imagine you have Gaussian noise applied together with rotations. So you can get quite massive degradation in the image quality because of it, and then nevertheless become invariant to those sort of transformations. What we show in the paper is that there is such a large pool of entropy inside of those auto augmentations that if all I do is I change the way you sample your randomness, I can force your model to learn things which completely don't exist in your data, like at all. And we can run similar attacks to the one we've seen with the reordering, but to a much stronger degree. Basically, just by changing the sort of transformations applied to the original images, we can force your models to, again, learn things that don't really exist in your data. So to give you an example, you see in the middle of an image where after augmentation, an 8, which looks definitely like an 8, can start looking a lot like a 0. And by the time it went through an augmentation, obviously, it changes its internal representation. And although you originally put it there in order to become invariant to, in this case, Gaussian blurring, actually you end up introducing backdoors into your models. And all you needed to do to make this work is just change your randomness, nothing but randomness. And picking this randomness is actually not complex at all. There are many other different ways to do it. In the paper, we show other types of backdoors, which rely on basically a similar principle. All we do is we change the way randomness is applied, and this is enough to then introduce backdoors into the models that are flowing down. And then finally, within the randomness space, we have released the paper with Pranav, who was a master student of Ross over the summer, where we looked at randomness attacks against randomized smoothing. But actually, it's more about Gaussian noise sampling. So randomized smoothing, for those who are not familiar, it's one of those standard techniques that is used for both security and safety. For security, people use it to counteract adversarial examples. And for safety, people use it to quantify uncertainty. They don't really call it uncertainty quantification, but this is literally what it does. And the basic principle is quite simple. sorry, let me jump here first. The basic principle is quite simple. Imagine you have a data point D, as is shown on the left here. What you can do is when you make a classification first, you can say, okay, let me take this classification and then apply a noise of a certain magnitude to it so that it shifts a little bit from its original location, and then you classify it again, you get the prediction and you get a confidence change, and you keep on doing this until you can estimate this epsilon, where basically what it says is, I am confident up to an epsilon that when an epsilon noise appears on top of this data point, it will not change its prediction. And fundamentally, this whole process depends on sampling quite efficient Gaussian noise. This sampling Gaussian noise, although it sounds like a very simple task, actually in principle, it's very, very far from being simple. And as you can imagine, an attacker who can change the way you sample this noise, as an example, for example, on the right, can force a defender to completely misestimate the actual true epsilon and force them to estimate another one. So imagine you have bias and noise, which forces the data point to be shifted more towards the left and a lot less towards the right. And then an attacker who would try to estimate the actual magnitude epsilon is going to misunderstand it. An important thing to realize is that when people talk about sampling noise and random noise, we don't really have any means of actually sampling randomness. With our computers, we have something called pseudo-randomness. We look for ways that give us enough entropy so that whenever you sample it, you ask a question for the next bit, it kind of gives you something that looks rather random. There are a lot of different takes that people rely on to make it work. Think about it like take a bad cipher, and then you give something that looks pseudo-random, and then as you pass it through a fake, like a relatively bad cipher, you get some sort of performance out of it. Given that many of those applications require uniform noise, especially at the beginning of computing, we required uniform noise for many things. Our modern hardware allows us to sample uniform noise by, for example, inverting diodes, as an example. And then, given that we mostly rely on Gaussian noise in machine learning applications, like, for example, with randomized smoothing, there are many fundamental algorithms you can find. And those things were described even by Knut. And many of those algorithms actually still stay the same. But the fundamental reason, the fundamental algorithm involved inside is we have an expectation of what a Gaussian noise looks like, and we try and approximate it by stacking uniform noise together, using here something called the wedge tail method. And basically the way it works is you, by square, try and approximate certain volume inside of your Gaussian, and by sampling it quite a lot, you can actually get yourself a representative Gaussian sample. And this is how it works under the hood. When we talk about sampling some Gaussian noise, nobody's really mentioning that the method they rely on, or the reliability of such method, or what it means to attack the actual randomness involved into sampling the Gaussian noise. And this is what we look in this particular paper. We change a single bit out of every 64 bits that pass by. And so that you realize this change is so small that when we run NIST certification, so NIST has the benchmark suite of tests for randomness, where they want to make sure that the overall statistic of your bit string is preserved. It kind of looks uniform. When we change a single bit out of 64, most of those tests, at least according to the official suggested number of samples collected for the test, we actually pass them. So we produce a totally NIST-certifiable backdoor random numbers generator that, as I will show in the subsequent slides, actually completely breaks randomized smoothing in many ways. I do want to mention that there exist other ways of doing Gaussian noise generation, and then those who are interested in this, they can see it in the link I posted just below. All right, so in this work, we show 3 attacks. I do want to say once again that we change only a single bit every 64 bits. We show 3 attacks, something called negative kurtosis, positive kurtosis, and skewness. And in essence, they look like this. In yellow, you have an expectation of what a Gaussian should look like if it was sampled. And then in blue, we show you the empiric distribution, where you can see that it ranges anywhere from this beta equals 0 for skewness, where it completely cuts a half of it and moves all of the volume to the right, into something that looks extremely similar, as for example, with alpha equals 2 and negative kurtosis, and you lose some volume around the mean. And similarly, for gamma equals 1, you observe that your tails lose some of the volume of the expectation. And as you can imagine, if you're running something like randomized smoothing, where all of the noise is more around the support of your distribution, more around the mean of your distribution, and you have a lot less sample from the tails, you are going to be overestimating your predictions quite clearly. So sorry for throwing numbers at you. It doesn't really matter what it shows. The important part is the one that I highlighted on the right. What we talk here is the maximum deviation from each of the individual attacks that were described before, with, again, just a single bit changing out of 64, where the R dash is the basically attacked radius, estimated radius, and R is the true radius. And we show here that by just changing a single bit, such that, again, it passes you a missed benchmark of tests, we can force your randomized smoothing to overestimate the true confidence, the true epsilon, by up to 81 times. And it's worth mentioning that actually, if we target specific tests more precisely, we can push this number even further. And this is because of how hard it is to even build an expectation of what a random number looks like. And the other thing worth mentioning is running those tests, the benchmarks for randomness is taking hours. It's not something that is simple. And given how much we rely on randomness sampling out of our machine learning models, so think about how much Gaussian noise we need to sample to train something like a stable diffusion model. It's quite insane. We rely on it a lot. We never test for it. It's infeasible to even test for it. And then obviously, inevitably, we have to trust it to make it work. In the past, we had cases where some actors performed attack using randomness. For example, there is a famous case where NSA backdoored randomness in order to break cryptography on top of it. And similarly, if tomorrow we're supplying our randomly backdoored hardware to someone so that we know that any sort of Gaussian sampling is affected, then it's going to be really hard to deal with this stuff. And inevitably, we have to run. So hopefully, after talking about those 3 examples of randomness attacks against machine learning, I've convinced you that randomness as a small foundation bit of our machine learning pipeline is important and can actually be used to break machine learning on top of it. So now I wanted to turn attention to Alchemy, or something I call Alchemy, namely the neural architectures. The reason why I call it Alchemy is because nobody knows why it works. It's truly magical. If you ask a question, why does this flavor of transformer work better than this flavor of transformer, people will be like, well, because. And this is a massive problem, because if we cannot tell why one thing works better than the other, then don't be surprised when tomorrow you find backdoors inside of it, or some unwanted behaviors that you never anticipated to even see there, and then you see your whole pipeline breaking. So here I'll talk about a paper called Architectural Backdoors inside of neural networks. This is work mostly done by Mikkel Weber-Irizar, who was a bachelor student of ours at the University of Cambridge. This work appeared at CVPR this year. What we do is something rather simple, bluntly obvious if you ask me. We take a normal AlexNet, as you can see on the left, and we add a simple component to it. We add a shortcut from the input to something we'll call a trigger detector, and then we fuse it back into our model. Our trigger detector is not something sophisticated, and it's not something that even has any parameters inside of it. It is using only standard machine learning components, and actually in this case it is listed on the bottom. It's just an average pool with an exponent inside of it. All of those are first-class citizens of the language, as for example, PyTorch. And that means that they do not look very odd inside of your model definitions. As a matter of fact, you will find similar structures in many different places. But once we've added this weird construction inside of our model, what we show is that we can expect any models trained with this architecture to then exhibit a very odd backdoor behavior. Think about this as us manipulating the implicit bias of an architecture where we never explicitly even told it what this implicit bias is. Such that when you take an architecture, randomly initialize it, and you train it, we show that badnets doesn't work, handcrafted does not survive. So So in this particular experiment on the right, we first initialize the network with a network which is either backdoored by nothing, backdoored by badnets, or backdoored with a handcrafted backdoor. All of those completely disappear once you start training another task on it, whereas our architectural backdoor, which is literally just two added average pools, it survives through training. So you can have backdoors that exist inside of the implicit bias of your architecture, and you will not even be able to tell that it's misbehaving in one way or another. To give you an example, so we do multiple different constructions, something called naive construction, and a more complex construction in order to target just white boxes in images and checkerboard triggers. So basically a white box trigger and checkerboard triggers. And we show that because white box triggers appear in some data, you get some sort of training performance, as you can see in the central image in the middle. And at the same time, the checkerboard trigger is not really noticeable. It's not activating anything. And you can see that once we add the trigger and we train our model with our modified additional shortcuts of the average pools, then it forces the model to lose performance consistently. And even if you retrain it to use any sort of other task, it always exhibits this behavior, as we demonstrate in the paper. And I kind of suggest this particular paper is that next time when you download a model definition from your Hugging Face library, and it gives you very nice performance on a given task of choice, this is not an indicator that the backdoors don't exist. And even if you retrain something from scratch, it doesn't actually mean that all of the backdoors are gone. As a matter of fact, your backdoors can exist in such inconspicuous things as just incorrectly placed average pool somewhere. At the same time, we have also produced a paper with Tim Clifford, who was a summer student of ours, looking at the types of backdoors that machine learning compilers can introduce into the models. So think about this in a way that you did everything correctly. You made sure that there are no backdoors anywhere inside of your data or in your model architectures. And then you take your model, you send it down to TVM as your model compiler, and then it gives you a model, and then you're happy because you made sure that everything works in your data. There is no backdoors there. Nobody changed anything. You go and you deploy it, and it still exhibits backdoor behavior. Well, this can actually quite easily happen, as we demonstrate in paper ImpNet, where we show that we can backdoor compilers in a way that they actually add backdoors of your choice. You can have actual compiler backdoors where we add additional executable pathways, as we show on the left, where you have an additional backdoor detector that basically takes over and adds malicious output as an output of the model. And then deploying these things is very easy. And if you try and go and decompile your binaries, you discover that actually it's insanely hard to discover that the backdoors were even added, because after you actually perform lowering and compilation process, because of all of the optimization, your model with and without backdoors looks insanely similar. And even if you know what you're looking for, it's really hard to identify it. And also we show that when you use compilers, you can actually construct something that you can't construct anywhere else, and what we call temporal backdoors. And this is an idea that you can have shared memory buffers inside of your definitions, and you can have parts of your model execute faster than the other parts. So in this case, on the right, we show that you can read the input, see if the trigger is presented, and if you observe the trigger, you wait for the main model to finish, and then you override the result with the backdoor result. And this thing happens dynamically at runtime. so it executes. And the backdoor activation itself is the speed at which the trigger detection itself is happening. And we build those things and show that it's completely possible and you can execute those things. And even if you do everything correctly as a machine learning engineer, you cleaned your data correctly, you did everything you could to debias your training regime, you can still be extremely vulnerable because you relied on a compilator built by someone else. And it's not like you can go and debug it, because many of those parts are completely non-trivial and rely on non-invertible transformations. So I hope at this point you realize that the architectures, we have to trust them because they're Alchemy. Compilers, we have to trust them because they're way too complex. And it's unclear what we even can do. Some of those attacks we can stop by carefully building defenses against those, but there is no general one-size-fits-all solution to any of this stuff because of the sheer complexity involved inside. And obviously, you end up having a completely compromised machine learning model despite doing everything correctly. How can you protect against randomness issues? I also wanted to note on some work, which I think is absolutely truly amazing from other people. This paper came out, I think, earlier this year from Nicolas Carlini, where what they showed is for some of the massive data sets, they have the way those data sets are distributed is people distribute a set of domains, and then you go and you query those domains to actually get the data. And what people discovered in this paper is that for a fraction of those domains, basically they expire and people don't renew them. And then they went ahead, they bought those domains and started sharing data sets with backdoors inside of them. And then they show that people nevertheless download those data sets. Nobody does any sort of hash checking. And inevitably, in this particular case, Nicolas Carlini and co-authors end up poisoning the data of others. And given that our data sets keep on growing inevitably and models are becoming bigger, it's foreseeable that such practices are going to keep on happening, and we're going to be distributing our data even more and more. And that would mean that provenance and trust into the actual distribution networks and trust into PKI to work correctly is going to be growing, as in the private key infrastructure. And this is something that nobody is really talking about except for Nicolas Carlini and co-authors. And this is absolutely a mind-blowing paper. At the same time, I think one of the coolest papers I've read a year ago is from Huama. It's not a widely known paper, but I think it's absolutely amazing. What people do here is they train models in a way that when a model is executed on full floating point range hardware, so think like if you have your general purpose computer and you're training a model there and you're using a model there, it exhibits one behavior. But once you quantize it or run it on hardware which does not have the same computing capability. So imagine you try and go and deploy it on top of an FPGA somewhere in the data center in order to scale it. It exhibits a drastically different behavior because it quantizes. So an example they give here is that you can have a class at 10.8 and you can have a separate class at 11.2, but once you quantize it, they both fall within the range of 11, and then they get classed very differently. And if you can imagine looking for such backdoors, it's practically impossible because there are infinitely many quantization ranges. There are infinitely many representation decisions. You can have floating point error buffers inside of your hardware, which keep on changing, and depending on the temperature in the room is going to be giving you drastically different behaviors. And clearly, this is yet another example of you necessarily trusting the hardware to do the right thing, and testing for such behaviors is going to be almost impossible. So to just sum up this idea of this MLCS pipeline is that it sounds simple. We talk about replication, we talk about securing data, cleaning data, building architectures. It all sounds simple, but even this simplicity is insanely complex, and so complex that dealing with it is almost impossible. Many of the attacks that I talked about are really only visible at the level when they're inserted. Like imagine your backend IR is actually inserting you the backdoor inside of your code, right? The temporal backdoor, as in the case of internet. You will only be able to see it once you've deployed it. Maybe if you manage to actually go through the runtime graph, or perhaps the ahead of time compile stuff, right? But these are the only 3 places where you will see it. All of the other parts that you usually outsource to someone else are not going to be able to even tell anything. And if you wanted to have any sort of provenance or any sort of confidence in that you're deploying what you actually want to deploy, you cannot get it unless you have provenance through the whole system as a whole, not just a small part of it. And that means that it's really, really hard to get it right, especially given that our compilers, like we have no expectation of what's going to be coming out of them, especially if we rely on a lot of those handcrafted heuristic optimizations inside. Right. And there are, importantly, I think, many unexplored points in this plot. So if you were randomly to pick a plot in here, pick a number or pick a letter and say, ooh, can I run an attack against this thing? Probably the answer is yes. And probably there is no paper even looking at it as of yet, especially if it falls outside of the data or architecture boxes. So let's go back to the original question. What is the machine learning TCB? And the answer is, well, nobody really knows. I'm sorry if I disappointed any of the listeners who expected an actual solution to the problems. There is no solution. Nobody knows. We are dealing with machine learning where we have no expectation of what it's even supposed to be doing. We can't test it. We don't have any expectation of, what's going to happen now to distribution, what's going to happen in distribution. We don't know what's going to happen if we change our floating point representation. And because of it, even defining what we trust is really impossible. At this point of time, I think it's fair to say we trust everything, but this is only going to give us insecurity and nothing but. It's clear that trusted computing base consists of both computer science, i.e. the infrastructure, the classical computer science, and machine learning security. And it's definitely going to include the interaction between computer science and machine learning. But as of right now, our TCP is basically everything of it. Maybe we can take some of the data-based exploitations, like adversarial examples, and say, well, to an extent, we can do robust training already, but everything else is clearly outside of anything that we can claim confidently that we have secured against problems, and all of this stuff we trust. And this is a horrible position to be in, especially if you expect your adversaries to attack you soon. Right. So the main lessons is, attacks will happen across the whole pipeline. If you think you protected data, this does not mean you protected your model. Most probably, you're overconfident, and that's a bad thing. All of your interactions between machine learning and the infrastructure are completely non-trivial. Like reliance on randomness, as an example, breaks many applications on top of it, right? And affects your pipeline in many different ways. And how to track those things, how to test against them, it's completely unclear. And inevitably, you will have to trust it. And defenses are not just about machine learning. It's about machine learning taken together with computer science, and the interactions that should be taken into the consideration. And I think the most important out of those things is that we need to remove the stigma from computer security literature about machine learning, and the stigma from machine learning about security, where security people say that some parts of the literature are not really security and have nothing to do with it, and rather start being productive and holding productive conversations about what should be happening and how to make our systems better. And that's basically it. Thank you very much for listening.
Thank you, Ilia. Luca is also sending applause.
So thank you for the presentation. It's question time. So first we're gonna give like a spotlight to the Zoom chat. So if somebody has a question, please raise your virtual hand, and I'm gonna give you word. otherwise, while we wait, I already have a question for you.
Sure.
So first of all, it's really nice to see, like, the study of security of machine learning is just like a whole, it's a whole discussion, is not just based only the model, or rather the security is basically like combining things. And about that, I had a curiosity about when you convert models with, like, let's say ONNX. So in your opinion, how much ONNX might be a huge security problem when you convert, like, for instance, from PyTorch to TensorFlow and other?
Yes, it's massive, actually. If you read through the ImpNet, we give a number of citations there. There is an amazing paper that came out, also not that many citations, I don't think there are many reads, called Metamorphic Testing of Compilers. And they do an amazing job of showing that you can systematically look for incorrect translation between non-adversarial transformations across the different representations of models, and they show that they've discovered a handful of them by running their metamorphic framework for a little bit. I'm sure if you sit down and by hand build some of those things, you can actually exploit this quite easily. Yeah, okay. It's massive. As a matter of fact, I think the compiler part, the ML compiler part, is full of completely unexplored directions. There are, like, you can do such things at this level of the stack that you cannot do anywhere else, and we have no means of securing it at all. Because, like, if in normal classical computing we have an expectation, for example, that semantically this transformation should give you something, then in case of machine learning we do not even have this. So an example here is, imagine you did some transformation that practically shrank, like, rather than out of transformation getting a whole output domain, like imagine your output domain of a function is 0 to 1, but you changed your representation that you are setting out from 0 to 0.8, so you lost those additional 0.2 things. When you try and estimate performance of your model just by saying what class it is, most probably you will not even see anything because you just project it onto something. But internally, everything has changed. And if right now at your point of the pipeline you don't see any change, then as it propagates down.
Wow, that's super interesting and at the same time super worrisome. So thank you. Thank you for the answer.
But I hope this makes sense, right?
Yeah, it made a lot of sense. No, it made a lot of sense.
And I think in this regard, the paper I mentioned towards the end about the quantization backdoors, I think this is just mind-boggling. I'm surprised people don't scream and shout about this, because the sort of problems you can do just by targeting specific hardware or constructing models for specific hardware is like, wow, you can do a lot.
So are there questions? Oh, yes, please, Professor.
Yes, thank you. Very nice and interesting talk. My question is about uncertainty quantification. You mentioned it, and maybe it's not your main focus, but just to understand how this kind of attacks may affect also uncertainty quantification. Uncertainty quantification?
Yeah. So, I mean, you've seen an example with Gaussian noise and randomness-based attacks. So I think randomness is probably one of the only ways that, well, maybe I'm wrong, actually. Yeah, I'm probably wrong. So long story short, when we talk about uncertainty quantification, the randomness attack is clearly doing this, because randomized smoothing, especially if you think about randomness smoothing in the limit of queries, this is literally uncertainty quantification, uncertainty with regards to the input. So you noise the input, you observe the changes, and this is your uncertainty. We know for a fact that people rely on this already out there in deployment. So, and I'm not sure whether there are any standards or requirements on machine learning PRNGs. So to the best of my knowledge, they don't exist. So yeah, I think there is a direct definition. And as a matter of fact, in the paper, we argue for creation of a new machine learning standard for machine learning specific randomness. The other fascinating thing there is, if you look at the PRNGs that usually get shipped together with standard libraries like PyTorch, they explicitly reduce the entropy inside of the PRNGs to make them faster. So think about them as ciphers, right? So they shrink the cipher such that, because they need to sample it a lot, they say, oh, we'd rather take a security cost, right? But we make it fast enough in order to enable it. And yeah, I'm sure you will observe minor changes and major changes if you don't sample it enough.
Okay, okay.
But the bottom line, actually, I mean, if your uncertainty quantification is compiled with the backdoor compiler, and you can, it's a classic trusting trust problem. So it's not like you'll be able to do much. But the fascinating thing for us when we wrote the randomness paper was that we only need to change a single bit out of 64 in order to actually have completely detrimental effect on the tasks downstream, which expect your noise to have a certain shape mathematically. And then, yeah, and then stuff breaks.
Okay. So since we run a bit late, we're gonna just close not the event, but close the live recording. So we can go toward the closure of the event. So Maura, I'll leave the stage to you to do the final remarks.
Yes. First of all, thanks to Ilia for this amazing presentation that is a lot of engineering, a lot of views that we don't usually inspect when we talk about machine learning, and I really appreciated the overview that you gave, and especially the conclusion with all these guidelines. So thank you a lot for coming to our event. Also, I want to mention that he shared the slides. I will copy again the link in the chat for those who are interested. And I have a little announcement. So the next event will not be in August, will be in September, because in August in Italy we take vacations. So I will see all the people again in September. So thank you all for joining, and now I'll close the streaming, and see you next time.